Hi there, good morning, good afternoon, or good evening, whenever you are, and thanks for attending this talk being virtual this year. I will be presenting our recent work about AndroLib to automatically recommend third-party software libraries for Android applications. This work has been done by Moataz, Chouchen, Ouni, and Mohamed Mkaouer, and this is joint work between ETS Montreal and Rochester Institute of Technology. Okay, so let's get started. So today Android has been the dominating operating system developed by Google for mobile apps, and Android is currently experiencing a huge expansion of its user base over the past few years. And in 2020 there are over 3 millions of Android apps that are available on Google Play Store, with more than 1,000 apps being published every day and more than 1.5 billion apps downloaded every month. And Google says that there are now more than 2.5 billion active Android devices in the world, which is a huge amount and a huge number of these devices. And all of these available apps are affecting the everyday life of billions of people, and there are actually several factors that contribute to the popularity and the expansion of Android, including its flexibility for vendor customizations, facility of integration of third-party libraries, along with other rich functionalities that are provided by the Android operating system itself. That is the development, the maintenance, and the evolution of Android applications. And this raises several other challenges for software developers, especially that third-party software libraries are becoming an integral part of the development of Android applications, since reusing them reusing such ready-made libraries can help in saving time and effort, and also it allows developers to avoid re-implementing functionalities that are already implemented and tested by third party. So today there are several repositories that provide high quality libraries such as Android Arsenal, Bintray, G-Center, and many other repositories that provide advertisement libraries for graphics, for social networks, for mobile analytics, and many other libraries that are ready-made for use and can be integrated easily in any Android applications. And indeed, recent studies show that over 60% of code in Android applications constitutes sub-packages from external libraries, and also 90% of Android apps use 5 or more libraries in their base code. For example, Arsenal or Android Arsenal constitutes more than 7,000 free libraries that are available for Android developers to be used. And developers need always to find useful libraries either in the initial development of their applications or during its evolution, as users always have high expectations and always asking for implementing new features. Apart from the rapid technology evolution of mobile apps, developers need to satisfy users to keep their apps useful and popular while competing with other apps in the market, which is challenging actually for Android developers to keep this challenge and continue to be competitive in the market. So here the real challenge for Android developers is how to find relevant libraries and useful libraries from the huge amount of available libraries that could be useful for their Android apps that are currently developed. So this can be difficult, time consuming, and also risky for Android developers if they select the wrong library that can impact the performance or the usability of their apps, and that can actually impact their users. So to address this problem, there are currently several approaches in the literature. Most of them, they focus on traditional object-oriented software systems like desktop applications or web applications, while at the same time there is little support for Android libraries. And most of the existing libraries, they use collaborative filtering or association rule mining or clustering techniques to find libraries that are commonly used together based on some specific datasets that are available, like for example Maven repository for Java libraries. And while these existing approaches have shown relatively good performance in recommending libraries or frameworks in traditional software systems, they are actually not directly applied or not customized for Android applications. In addition, one of the limitations is that these existing approaches mostly recommend libraries in an individual way. So while providing little attention to the innate or the existing relationships between Android libraries that need to be recommended together, like for example make some combined recommendation. For example, social network libraries and image loading libraries are typically used together, so that they need to be recommended somehow together, not individually, to make sense for software developers. In addition, due to the nature of Android apps, a small fraction of popular libraries actually dominates the market, while most of other libraries are less used. Indeed, focusing the recommendations mainly on library usage records may hurt other relevant libraries that are of good quality and that can be useful for Android apps. And as a consequence, newly published or in popular apps, in popular libraries, may have little or no chance to appear in the recommendation results. So this aspect needs to be considered for efficient library recommendation systems. And to address all of these challenges, what we propose is an approach called AndroLib. So AndroLib takes as input a query from a developer who is searching for candidate libraries for his application, and it takes also a snapshot of data collected from currently available Android applications and their used libraries, as well as their current user rating in Google Play Store, so that we can have an idea about which apps are more successful than others. So then the collected data will be encoded in a specific format as a graph. We are using a graph to record and to store all the data collected from open source Android applications. Then a multi-objective search algorithm will be used to explore such data and recommend relevant libraries based on different criteria, such as the libraries that are commonly used together, the functionality, the functional diversity among the recommended libraries, and also the user ratings of the apps that are that use the candidate libraries to be recommended. So in our approach, we use NSGA-II, the non-dominating sorting genetic algorithm, as a basic search algorithm. Then in the last step, the recommended libraries will be ranked based on their occurrences in the Pareto front. The Pareto front consists of a set of optimal solutions that are returned by the algorithm. So then the developer will receive the recommendation and will decide either to adopt or to ignore the recommended list. So before delving into the details, let me recall how NSGA-II works for unfamiliar people. So NSGA-II starts by the generation of the initial population in a random way. Then an offspring population is generated using genetic operators like crossover and mutation, and then the fit test solutions will be selected from the based on the non-dominance principle, and 50% of the population will be used to generate the next generation, and the process will be repeated until reaching the last iteration or when a stop criteria is reached. So to adapt NSGA-II to a given problem, there are different elements that need to be defined, like for example the encoding or representation of candidate solutions, the definition of a fitness function, the definition of genetic operators, and the generation of the initial population. So in the next slides, I will explain each of these basic elements. So for the data and solution encoding, our input data consists of collected Android apps and their used libraries from open source software repositories, and we use a specific graph-based encoding to facilitate their exploration in the recommendation module later. Then we use a vector representation to encode candidate solutions for NSGA-II, and each dimension in this vector represents a specific library from the pool of existing libraries for mobile apps. Then we use crossover and mutation in order to involve a population of solution. So crossover takes as input two solutions, two parent solutions. We are using the random and single point operator, which takes two parent solutions, then cut and merge them to obtain two new offspring solutions. Then for the mutation, we take as input one single solution, a parent solution, then we randomly select one or more libraries and replace them by other random libraries from the pool of existing libraries. Then finally, the fitness function is the most important component. We define three objective functions. So the first objective function is to maximize the recommended library co-usage. So we aim at discovering third-party libraries that are commonly used together by other applications. Then the second objective function consists of maximizing the diversity among the recommended libraries. So we want to have libraries with different functionalities, because recommending libraries with the same functionality could be not relevant for developers who are looking for different categories or different libraries. Then the final or the last fitness objective function consists of maximizing the reuse from successful applications. So here we want to increase the chance of recommending commonly used libraries in apps that have high user rating, while decreasing the chance of recommending libraries that are used by low rated apps. So it's kind of, we would like to learn from successful apps in the store. So to evaluate our approach, we basically define, or we aim to addressing two main research questions. The first research question is about evaluating the accuracy of our approach as compared to state-of-the-art approaches, and the second research question is about evaluating the performance of our approach in terms of the ranking of these recommended libraries, so that we can make sure that the first or the best libraries are recommended in the first ranks in the recommendation list. So we use a data set that consists of a set of 2,752 open source Android applications that use over 979 libraries. So the used dataset is also publicly available, that can be found in this in the link in the slide. And we also considered three recent state-of-the-art approaches: Crossrec by Nguyen in 2020, LibCap by Said in 2018, and LibRec by Tong in 2013. These are three approaches use collaborative filtering mainly, and clustering techniques in order to find and to mine recommended libraries based on their co-usage patterns. Also LibRec is based on association rule mining and collaborative filtering that are combined together in order to find relevant recommendations, and still it's based on the dependencies or on the co-usage of libraries in the data set. So to respond to the first research question, we are using as ground truth the experimental data set that consists of over 2,700 applications. We use tenfold cross-validation, and for each testing app in the test data, half of its libraries are randomly taken out, are randomly removed, that will serve later as ground truth data. Then we use basically three metrics: the success rate, which counts the number of apps for which at least one correct library is recommended, and we also use the traditional precision and recall. As for the second research question, we aim at recommending the quality of the ranking of the recommended libraries. We use the mean reciprocal rank, MRR, which measures an average rank of correct library that an approach can recommend. So ideally, we would like to have the first correct library is in the first ranks, instead of walking through a long list of recommendations to find the first good library. And in like MRR, the metric NDCG, the normalized discount cumulative gain, emphasizes on the precision of the first few recommendations. It looks at the first, to the second, to the third first ranks in order to evaluate how good are the first ranks that are recommended. So let's see the results for the first research question. So we found that AndroLib achieves better performance than the state-of-the-art approaches with a success rate of 91%, precision of 87%, and a recall of 81%, which are all statistically significant as compared to the state-of-the-art approaches with medium and large effect size in most of the cases. So on average, we have 78% of precision and 81% of recall, which are considered better than the state-of-the-art approaches and can be relevant in terms of practicality for developers in practice. And as for the second research question, in terms of the ranking performance, the first figure about MRR, the mean reciprocal ranking, it shows that AndroLib achieves a score of 0.72, while the state-of-the-art approaches are still under 0.66, 0.59, and 0.58 respectively for Crossrec, LibRec, and LibCap. So this indicates that our approach provides a higher chance of recommending appropriate libraries in the first ranks. In terms of NDG, we also observe from the second figure that AndroLib achieves better results in providing accurate library recommendations in the first few ranks, which are better also than the existing approaches. This could be due to the fact that libraries are recommending individually in the state-of-the-art approaches rather than considering their relationships and recommending them in a collective way. In addition, each of the state-of-the-art methods are mainly based on a set of similar apps to find libraries, while neglecting the success of the apps in terms of user rating. In addition to a key feature of AndroLib is that it provides appropriate diversity mechanism to avoid redundancies in the recommendation list, so that we have a higher chance of having correct libraries in the first ranks. So to summarize, we proposed AndroLib, which is an automated approach that uses NSGA-II, the non-dominated sorting genetic algorithm, and formulates the recommendation problem as a multi-objective optimization problem. We combined the historical usage of libraries, the diversity, and the rating, the success of the libraries. We conducted an empirical study on over 2,700 libraries and over 979 libraries. We found promising results with 78% of precision and 81% of recall, and we can recommend also libraries in the first ranks. As part of our future work, we will evaluate our approach with larger dataset from both Android and iOS applications. We also will compare the performance of NSGA-II to other search algorithms, and we are also planning to conduct a qualitative evaluation with Android developers. And thanks for your attention. If you have any question, please do not hesitate to email us. Thank you.